All right, we are ready to define the other three inverse trig functions. So we're going to be defining here at the bottom of the board arcsecant, arccosecant, and arccotangent. Okay, and of course, what each of these things means is if I've got y equals arcsecant of x, it means that x is equal to secant of y, and there's another condition because we're not going to be taking the inverse of secant, we're going to be taking the inverse of secant with a restricted domain. And that restricted domain becomes the range of the inverse function. So we're going to have that y is an element of, and what I want you to do in a moment is describe for me, fill in these three blanks with the interval or intervals that we're going to get in these definitions. Okay. Now, they're definitions, but instead of telling you what the answer is, I'm giving you the rules by which we decide what these intervals will be. Okay. Now we're choosing intervals. As I phrase the rules, rule 1 is to always choose quadrant 1. Of course, what I mean by that is the interval that corresponds to quadrant 1, in particular the version that corresponds to acute angles. So that would be the interval between 0 and pi over 2. Okay. I didn't have enough room to write out choose the interval that corresponds to a quadrant, so I just said choose a quadrant. Okay, figuring you'd understand what I meant. Okay. So here are the rules. You always choose quadrant 1 between 0 and pi over 2. You're always going to choose an adjacent quadrant, so either 2 or 4, and it's got to be where the trig function involved is negative, so that we have one quadrant, quadrant 1, where it takes on its positive values, and one quadrant, either 2 or 4, where it takes on its negative values. Sometimes that's going to be enough for you to figure out what your second quadrant is. If not, go to rule 3. If the trig function is negative in both adjacent quadrants, so we saw that, for example, with tangent. Tangent was negative in both 2 and 4. Then you're going to choose the one that gives you a connected section of graph. So we looked at tangent and said we get just one nice connected curve between negative pi over 2 and positive pi over 2, which meant we chose quadrants 1 and 4 for arctan. Okay. All right, and then rule 4 is just include the quadrantal angles, which are going to be the endpoints or the boundaries of the quadrants, if and only if they're in the domain of the original function. So for example, with arcsine, we had 1 and 4, and it was negative pi over 2 to positive pi over 2, described with brackets, because those two quadrantal angles are in the domain of sine. But arctan, we chose the same, almost the same interval, from negative pi over 2 to pi over 2, but we had to use parentheses because those endpoints aren't in the domain of tangent. Okay, so I want you to pause the video and see if you can find the interval or intervals to fill in these blanks. And we'll go over that together when you turn the video back on. So I've erased the written rules here. We'll just be hopefully remembering them. And I've just drawn in a picture of the quadrants. And I went ahead, crossed off quadrant 3. I might as well circle quadrant 1 because our rules tell us we always choose 1 and never choose 3. So it's always 1 and 2 or 4. If we're working with arcsecant, okay, I need to choose as my second quadrant either 2 or 4, the one where secant is negative. Now secant's the reciprocal of cosine. That would be positive in 4, but it's negative in 2. So we're going to choose quadrants 1 and 2. So that would be the interval from 0 to pi. I do need to be very careful there. 0 and pi are both in the domain of secant, but pi over 2 is not. Okay, so I'm going to have to write this as a union of two intervals. From 0 to pi over 2, union pi over 2 to pi. 0 and pi get brackets, pi over 2 gets a parentheses. Okay. Now, that means I've got two separate intervals. Not ideal, but there's really no way to avoid that with secant. If I look at the graph of secant, where these asymptotes are at my odd multiples of pi over 2, there's no way I can restrict the domain, get the part of the graph that's positive and part that's negative, and have it connect, because the positive part doesn't touch the negative part. There's this no man's land in here between my y values of -1 and 1. So the positive part and the negative part that we're getting aren't going to touch each other. So I just have one interval for the positive part and one interval for the negative part. Okay. So in general, the advantage of choosing either 2 or 4, I think the main advantage is that that usually allows us to get just a single interval. We're going to lose that advantage when we work with inverse secant and inverse cosecant. Now there is still an advantage to going with the rule that we always choose an adjacent quadrant. That's that if I look at the range, the restricted domain of cosine, which becomes the range of arccosine, it's the interval from 0 to pi. This is almost the same. We just have to remove that one quadrantal angle that wasn't in the domain of secant to begin with. So I'm preserving a connection between secant and cosine when I restrict their domains. I should warn you, though, that the rules that I wrote on the board are not universally agreed upon. There are, in fact, 2 accepted definitions for inverse secant and inverse cosecant. I presented the rules and the definition that's in our textbook, and this is consistent with what was in the textbook from trigonometry that you probably took last semester if you took that here at Saddleback, okay? But because we don't get a connected piece of graph when we restrict the domain, because we're going to have 2 separate pieces anyway, the advantage of having an adjacent quadrant isn't quite as strong when we're talking about secant and cosecant. For that reason, some textbooks drop the rule that you have to choose an adjacent quadrant, and in defining inverse secant and inverse cosecant, those textbooks will use quadrants 1 and 3. Not obvious why 3 might be preferable. I actually think it's the better choice. At this point, not at all clear why that makes sense. It kind of seems like a wacky choice to make, okay? We're going to get there, okay? We will actually take a look and see why some people prefer to choose quadrant 3. Even though I think that's the better definition, I'm going to respect what your textbook does, but I'm warning you about this for 2 reasons. 1, this is pre-calculus. Most of you, I'm assuming, are going to go on to calculus. Our calculus textbook was written by a different author than our pre-calculus textbook. Guess what? The definitions of arcsecant and arccosecant will change when you go into calculus. Different textbooks made different choices about the definitions. Okay, so be prepared. You need to know the definition that we're using this semester, but be aware that it will change next semester when you're in calculus. Okay, second reason it's important is that this is a community college, and many, if not all of you, are planning to transfer to a 4-year school. Now, when you transfer to a 4-year school, who knows what textbooks they've used for their calculus classes? So in your in any math classes that you take there, you're not going to know which definition of inverse secant and inverse cosecant is being used. You're going to have to either look it up in the textbook or ask your professor. So it's important to know that there are 2, both accepted and considered correct definitions for arcsecant and arccosecant. Huh, so complicated. All right, let's move on to arccosecant. So I'm going to erase the circling of 2, but I'm going to keep 1 circled because we always choose it, and I'm going to keep 3 crossed out because with this textbook we never choose it. Okay, so I'm choosing quadrant 1. I need either 2 or 4. I need the one where cosecant would be negative. Well, cosecant's the reciprocal of sine. Sine and cosecant are positive in 2, but negative in 4. So we want 4 and 1. That's from negative pi over 2 to positive pi over 2. But again, be very careful. Negative pi over 2 and pi over 2 I can include because those are in the domain of cosecant, but 0 isn't. So we'll have negative pi over 2 to 0, union 0 to pi over 2. All right, excellent. Let's do inverse cotangent. Okay, so we choose 1. Now cotangent is one that's negative in both 2 and 4. So we run into the same issue we ran into with tangent, that it's negative in both adjacent quadrants. So here I need to go to my graph of cotangent Remember, that had asymptotes at all multiples of pi. So there's an asymptote at 0 and at pi, and again at 2 pi. There would be one over here at negative pi. So I can see if I choose this interval, here's 0 to pi over 2, that's the interval I always choose because that corresponds to quadrant 1. If I choose from pi over 2 to pi, which would correspond to quadrant 2, I'm going to get a connected piece of graph. And of course, I'm not going to include either endpoint because those aren't in the domain of cotangent. So cotangent, we get the interval from 0 to pi, and it's an open interval. All right, good stuff. So we've got these definitions down. Now, hopefully you were able to figure those out based on those rules that I gave you. And I think being able to figure that out is much more important than having these results memorized. So I will probably at some point ask you for this information in some way, shape, or form. I could ask you to give me the range of the functions. I could ask you to fill in the blanks. But I'd encourage you to understand why we're making these choices in doing these definitions. Okay, I'm going to just put 3 problems up to evaluate some of these new inverse trig functions. Give those a shot before you tune into the next video, and then we'll go over those together. Okay, so let's try arcsecant of -2, arccosecant of 0, and arccotangent of -1. Okay, so try evaluating all of those. The next video we'll go over those together.